Okay, good morning.
Good morning.
So, let us see everything is right here. Yes. So this is a lesson that you usually need to use GeoGebra, probably, but we want to explore the relation between the graphs of the functions f prime, and f double prime. So see that how it works. Let us start understanding this connection a little bit from very simple examples, yes? So assume that I give you a function. Let us start with a very, very simple one. The equation of a line, for example. So here, for example, let me consider a line that passes through the origin. For example, if this is 1, this is 2, and then you have this straight line, yes? So this is 1, this is 2, and you have this straight line passing through these 2 points. Yes? F of x. Y equals to f of x. Of course, in this case, it is very simple. If I ask you what is f of x, in principle, you should be able to answer that, because that is an equation for the line that passes through 2 points. You can read the m value of this line is, of course, 0, and the k value is 2 units. So you can really understand what is f of x. And then you can take the derivative of that. It becomes a new function, and you can draw the graph of the new function. But the point is not to do this. The point is to be able to understand the graph of the derivative of the function and the second derivative. Of course, this is not always easy, but we want to explore qualitatively the connection between the graphs of the functions f prime, and f double prime, if possible. Yes? Okay, so can you predict how will be the form of the graph of the function? Let me just repeat again. In this case, if I ask you, can you tell me the formula for f of x explicitly, the answer is yes. You can write that formula, take the derivative, it becomes a new function, draw the graph of the new function. You take another derivative, it becomes a new function, draw the graph of that function. So you immediately realize what are they. But if you don't want to do it explicitly, is there any way qualitatively answer that? At least the general aspects of f prime and f double prime. So how do you look at the problem? Because there is no new lesson here. We just want to explore the connection between the relation between f prime and f double prime as graphs based on what we have learned so far. Okay, so do you have any idea? For example, one way to see is this function increasing or decreasing? This function is all the time increasing, so its derivative should be positive. So it means that you do not expect something like this. So if I ask to draw the graph of this, you do not. So if I say that this is the graph, of course I don't want to. So this is the graph of the derivative, you immediately say that no, this is not possible. Because here I see that the function is always increasing, so its derivative should always be positive. What does it mean? It means that it should be always above the x-axis, yes? But now you see that some part is below the x-axis. So something like this cannot happen, for example, for this function, yes? These kinds of arguments you want to train yourself to understand. Okay, so one way to look at this problem is that this function is a linear function, so its derivative should be a constant. So what do you expect for the derivative, the graph of the derivative? Yes?
Horizontal line.
A horizontal line, yes? But which horizontal line is important? So you realize that the graph of the derivative is a horizontal line. But a horizontal line could be the x-axis. It could be y equals to 1 axis. 1 equals to 1, y equals to 1, y equals to minus 5. Or which number is it important here? So which one is that? Yes?
Y equals to 2.
Why?
Because it's always increasing by 2.
So yeah, the slope, because the derivative, what is the geometrical interpretation of the derivative is the slope of the tangent line. And if you have a straight line, it doesn't matter which point you choose, the slope is always the same. And what is the slope in this case? Because you have here you have 1 unit and 2 units up, so hopefully you understand that slope is 2. So if I ask you to draw the graph of the derivative of the function without going to the process of finding the function itself, is to draw this, yes? 1, 2, and this becomes the derivative y equals to f prime. So it was very easy that without going to the process of finding the function and differentiate it and draw the graph of the derivative, hopefully for every one of you is clear that that would be the derivative, the graph of the derivative. Yes? Okay, what is the derivative? What is the graph of the second derivative? Yes?
Would it be the same but on 0, like completely on the x-axis?
Yeah, it is. So forget, now give the role of f to this function. Yes? So you see this was the function, this was the first derivative. Now if you want to go to the second derivative, you can imagine this is your original function and you want to do the process once more. Yes? So what you are supposed to think about is again the slope of this. Okay, what is the slope of this line? Everywhere it is 0. It's 0. So the second derivative which gives you the slope to the first derivative. It doesn't give you the slope to the first function. It gives you the slope to the first derivative. The slope to the first derivative is 0 everywhere. So you can realize that the graph of this function is actually, I don't know how to draw it. You need to draw it here. So let me change my color. This is y equals to f double prime of x. Usually it is common to draw all of them not on 3 different coordinate axes, but just in one. So usually you draw all of them in one coordinate system, probably with different colors, for example in GeoGebra, to be able to differentiate the graphs of it. So is that understandable? So qualitatively this is the way, and that's actually good to understand, okay? So one thing is now very clear. I want to ask one question. If I take the same line and draw it from 2 instead of 0, but parallel to this one. Okay, so what I'm saying is that imagine that instead of having this line, I have started from this line, but parallel to this. Okay? So what will be the graph of the derivative of this dotted function?
The same?
The same. Yeah, so because even though this function is different from that function, but the derivative is not sensitive to the exact location of the graph. It is sensitive to the slope of the tangent lines. And hopefully you agree that there is no difference when it comes to tangent lines and slope of tangent lines between this and that. So the derivative is exactly the same. And the second derivative is exactly the same. Yes? Is that understandable? What happens if I change the line from this to that? For example, I take this. Let me change my color so that you are not confused. This is the second example, but the answers were this. So now let me take this line. If the green line is the graph, what will the graph of the derivative of this green function? Yes?
Never mind.
Y equals to minus 2.
Minus 2. But because now the slope is minus 2, do you agree? When I move 1 unit to the right, the y value drops by 2 units. So it means that the slope is minus 2. So then it means that I have to draw the same thing, but from 2 now, I have to draw it from minus 2. What will happen for the second derivative?
It will be the same.
It will be the same. Yes? So these kind of things you have to understand. And then, by the way, you see that the derivative is always negative here. Why? Because the function is decreasing. When I go to the right, the y value goes down. So this means that the function, the green function, is decreasing. And that is, you see, also is consistent with what Robert said, because the graph is always y equals to -2 and it's negative all the time. Yes? Okay, but the question can be a little bit complicated. Let us make it a little bit by going to another example. So let me tell you that. Let me take the example in the book. So they have a parabola here. So it is -1 minus. So let me write it like this. So it is just -4 here, and then you have it +2 and -2. Yes. And I mentioned myself that assume that this is a parabola. Because, for example, why I have to mention that, if I draw the graph of x to the 4, what will happen? I put 0, it becomes 0. I put 1, it becomes 1. I put -1, it becomes 1 again. But if I put 2, it becomes suddenly 16. So it becomes more or less very similar to the parabola, but it is not a parabola because it is of the 4th degree. So because the graph looks like a parabola, you're not allowed to preassume that this is parabola unless it is explicitly mentioned in the problem itself. And I am explicitly mentioning it here. I am telling you, assume that this is a quadratic function. But which function, we don't know. We have only these information. We know that this is a 2nd degree polynomial and then passes through these 3 points. Again, if you insist, you can find the function explicitly, yes? Because you know that when I say it's a parabola, you know that the general formula is this. And how many pieces of information is missing? A, B, and C. And how many pieces of information is provided for you? 3, exactly. Because this is supposed to pass through these 3 points. Each one piece of information gives rise to an equation. Then you will have 3 equations, 3 unknowns, and you have to solve them and find. Yes? But the point is not to do that. The point is to understand the connection, the relation between the graph of functions and their derivatives. Okay, so what is your idea about this one here? So let me just try. To do another sketching here. Yeah. Again, assume that this is a y-axis. I want to draw it in the coordinate system. So, okay, what is your opinion about the graph of the derivative? Definitely the graph of the derivative will be what type? It's a parabola, so its derivative should be a line. Yes, a linear. Yes, because if I take it doesn't matter which parabola I am facing, whatever it is, if I differentiate it, it becomes 2ax plus b. 2ax plus b is a line, yes? The k value is 2a, the m value is b. So you know that the graph of the derivative should be a straight line. Yes? What would be about the 2nd derivative? Yes?
It's not existing.
Okay, what?
It would be a horizontal line.
It would be a horizontal line, yes? Why? Because when I told you that, you know that the derivative of this is a line, so it has a slope. Its 2nd derivative becomes a horizontal line. Yes? But probably not 0. We have to see. Okay, so what line will it be? Just by using these pieces of information. Let me ask you one question. If I go and look 0 here, I am claiming that that line should pass through the origin. You tell me why. So you see, so these things that I want you to understand, if I give you the graph of this function, and I ask you to show that the graph of the derivative will pass through the origin, You should have a good reason for that. Yes?
Since there's a local minimum point, and at that point the slope is 0.
Exactly. So that's understandable. You see, this point, which point 0, if I ask you what type of point is this point for the graph of this function, it's a local minimum, yes? Yes, it's a local minimum. And you know that the derivative at a local minimum should be 0. But at which point, at which number it is happening at the origin. So by looking at this graph, I want you to understand that this is indeed valid. Yes? If I ask you what is the derivative of this function at the origin, you go to the origin, you find the corresponding point on the graph, you draw a tangent line and read the slope. But if you do this, because the tangent becomes horizontal, the slope that you read is 0. So it means that the derivative is a function so that at 0, it is 0. So it means that this point is definitely on my derivative. Yes? So it means that it should be a line. For example, if I draw that line and I say that, okay, do you think that this can be the graph of the derivative of this? You have to immediately rule it out because it is not passing through the origin. Yes? Okay, so let me ask you another question. By looking at this graph, if I have a line that passes through the origin, it might be in this direction with positive k value, or it might be in this direction with negative k value. Which one do you think will be suitable for this graph? Because we realized that this is second derivative. It is second degree. Its first derivative should be a line, and we convinced ourselves that this line has to pass through the origin. But we can consider two types of lines: the lines with positive slope, the lines with negative slope. By looking at this function, which one do you think is a good choice for that? Yes, Roku?
It would be increasing because there's a minimum value, which means that the A would be positive.
I don't want you to talk about equations. I want to answer these questions geometrically. Okay, let me ask you once more. Do you think this one is the case or that one is the case?
The increase.
So let me write number 1, number 2. Which
Number
one?
one.
Number 1.
Yes.
So you are saying that number 1 is the answer to this. So you say that this is the graph of the derivative.
Yeah.
Okay? Okay, can you defend yourself again?
Well, as I said, if we can see from the form of the graph that it has a minimum, and if it has a minimum, then the coefficient in front of x squared will be positive. We know that.
Okay, you are talking algebraically. That's
okay,
correct.
I don't know how to define it geometrically.
No, geometrically means using the concept of a slope and derivative.
Okay, in that case, I don't know. I just know.
Okay. Yeah. What about you, Robert? Do you have any comment on that?
I agree.
Okay. So let me tell you something. So in this graph that you are defending, on the interval from 0 to infinity, is the derivative positive or negative?
Positive.
So here the derivative is this graph. Above the x-axis, the y value, which is the derivative in this case, is positive. And below the graph, the derivative, which is the y value, is negative, yes? But look here, when I go to the right-hand side, what happens to my function? The function is increasing. So this means that by looking at the function on the right-hand side, I see the graph is increasing. When the graph is increasing, the derivative should be positive at that part. But this function is exactly the opposite, because on the positive x part, the derivative is below the x-axis. So the derivative is negative, so that is not working, yes? It should be a function of this type, because on the right-hand side, I see the function is increasing so I expect the derivative to be positive. I expect the graph should be above the x-axis. But now look on the left-hand side of the origin. What happens to the function itself? It is decreasing. So it means the derivative should be negative. So it means that if I go to look on the left-hand side, I expect to see the derivative graph below the x-axis. So hopefully you understand, based on this, without talking about coefficients, I can understand that this type of behavior should be the case. Yes, is that right? But can I draw the exact value? This is actually hard to say. Because if I want to find the exact slope, I really have to do calculations. So I don't think they can make it exact values unless they have, actually they have given it to GeoGebra, of course, then they have drawn it better. But I mean that what we can do is to draw qualitatively that this would be the graph of the derivative. But of course, there are infinitely many possible cases left, yes, because I might have this situation, that situation. You see, I have a lot of situations left. If I want to exactly know what it is, I really need to know the slope of the derivative of the tangent at each point, you know. So you see, this is not easy to say. Yes. Yeah. So that is not something that I can detect immediately. So that's why I'm saying qualitatively, you know that if this is the graph of your function, the graph of your derivative would be like this. Yes? But which one exactly, we don't know. If you really want, you have to have exact form of this. Otherwise, we cannot predict. But qualitatively, we were able to predict. First of all, we realize that derivative is a line, not a circle, not a parabola or whatever. We also learned, that is important, that it passes through the origin. And we also learned that this is with positive slope, not negative slope. Now, if I ask you what will happen for the second derivative, you have to do the same process, forget about the original function completely, and assume that this function in the beginning is given to you, and then you want to do it, this process that I described, once more. Okay, so how do you do that? This is a straight line. You know the slope of the straight line is a constant. So what does it mean? It means the second derivative will indicate that constant. Is that understandable? Because every time that we take a derivative, it gives you the slope of the tangent line of the previous derivative. Yes? So this means that this should be a horizontal line. But which line? Above the x-axis or below the x-axis? Yes?
Well, since it's increasing, that means that it has to be positive.
Positive. So it should be a horizontal line here. What exactly, where, we don't know. Yes? And then that's also squares with that. Do you remember I also told you the second derivative test? I told you that whenever you have a local minimum, the function is concave upward like that, like a real bow, yes? And then I told you that the second derivative should be positive, and then this is also indicating that. So the second derivative is positive. Okay, let me just do some games. For example, what happened, I haven't seen this example in the book, but let me just try to see what will happen if I have this parabola. So let us take a parabola like this, passing through the origin, then continuing, coming down. So let us take this one to be 4. Yes. Yeah, something like this is a parabola, so it continues forever. And then this is your x and this is your y. And this is, I am claiming that your function is a parabola. But which parabola, we don't know. We have this. And then if you don't mind, let me also give you this information. This number is 2. If you want, I can give you this information as well, but I don't think it matters here. So let me give this one. Okay, so let us investigate this a little bit. First of all, what will be the type of the graph of the derivative? Because I told you again, this is a parabola. Assume that this is a parabola. Yes?
A straight line.
It would be a straight line. Yes? So that would be a straight line. Okay. So yeah. So now, which type of line is that? So can you tell me a point that you are confident that the line will pass through? Yes. Can I understand that point? That was here. That was I was confident here. Yes. So yes.
Since you have a max point, the k value at the max point is 0, and so the slope of the graph of the derivative should cross the origo.
Not origo. That's the whole point. So it means that this is not sensitive to this shift. So you see here, this is the equation. You shouldn't get confused because these questions are a little bit confusing. Okay, so what you said is everything was correct. Your conclusion was probably a little bit wrong. So by looking at this, you said that I see it that is a local maximum. So what is so can you tell me? Can you feel this gap? What is this here?
2.
2. So you know that. Why should so? This is 2.
So it should cross 2.
So it means that your line. So this means the derivative at 2 is 0. Yes. So if you go and find the point 2 and 0 here, your line definitely passes through this because you yourself are telling me that f prime at 2 is 0. It means that the graph of the function related to f prime should be a function that passes through the point 2 and 0. Is that right? Is that clear? So this is now the point that your line passes through. But now I am asking you, do you think the line passes in this direction or in that direction?
That one.
This one.
Yes.
Why?
Because in the other graph, it was the other way.
Yeah, so let us consider. So let us explain why this is the case. So here, before 2, what type of function you are facing?
Increasing.
Increasing. So the graph should be above the x-axis. Yes? So that is the case. And if you go after 2, the function is decreasing. It means the derivative is negative everywhere after 2. So it means that the graph of the derivative should be always lower than the x-axis. Yes? So if you want to see, this is the graph somehow. But exactly what, we don't know. If I want to know exactly what happens here, can you tell me what should I know exactly? So you see, this is definitely one point. And I am telling you that, hopefully you agree with me, your line should be a line with a negative slope with the reason that I told you. But assume that you really want to find the exact line. For example, I need to know this point. For knowing this point, I need to know, so f prime at 0, yes? If I know f prime at 0, I need to know this point. So it means that I need to know a slope of this line, but I don't know, yes? Unless I do the explicit calculation. So this means that I cannot do that. And then what will happen for the second derivative? The second derivative would be a horizontal line, but on the positive part of the y-axis or negative part?
Negative.
Negative part, because the slope of this one is negative. And the second derivative will be the slope of the first derivative graph. Yes? Is that understandable? Okay. But there is a trickier question. The trickier question is that I give you the graph of the derivative and I ask you to anticipate something about the properties of the graph of the function. That is harder. Not harder, I mean that is a little bit counterintuitive. So let me before doing that, let us, if you don't mind, let me just continue this one more step. Okay? So now let me draw a graph for you, and I tell you that this is the graph of a third degree polynomial, and then we want to go to the first derivative and second derivative if we can, yes? Let us see how it works. So for example, let me just give you this graph. This might be you don't have enough knowledge exactly, but let me just try to see how it goes. For example, you have a third degree polynomial which goes like that. Yes, so this is supposed to be the origin, and let me make it -4, and then let me make it -2, and if you want I can give you this is 2, and then let us consider this to be 2, and this one -2, and this one +4. For example, I am telling you that assume that this is the graph of your function, and I myself emphasize that this function is a function of third degrees, a polynomial of third degree. So then you are supposed to find an equation for, it's much more fun now, yes, I think, if we can manage it. Let us see how it goes, yes? So you want to find the qualitative graph of the first derivative. So what type of graph you expect? Yes, Hossein?
Parabola, I think.
Yeah, a parabola. So it means that you are facing a parabola, yes? So what I'm supposed to do, okay, so let me just try to see what happens. So I will have this parabola, but what type of parabola? Because I might have a parabola of this type with maximum, I might have a parabola of this type with min. Yes, so what type of parabola you are expecting? So 2 points are important. First, tell me these things. There are 2 points that you should convince yourself that this parabola, either in this form or that one, should pass through. What are those points? Yes?
When x is -2, y should be 0, and when x is 2, y should also be 0.
Exactly. Why? Because at here, I have a local maximum. So if I ask you for the function f, what is the derivative at -2, you shouldn't doubt the answer is 0. And if I ask you what is the derivative at 2, this is also 0. Because this time I have a minimum. Yes? So this means that for the derivative function, the graph should pass through the point -2 and 0 and the point 2 and 0. So it means that I will go and find here. Yes, I will have these 2 points. Yes? So this means that I will face a parabola at which this will go in that direction or in that direction. Let us see which one is which. Okay, so let us, for example, momentarily think that this is, I don't know which one is which, so let me just guess. That's positive. Okay, so let me make it the other way around. Do you think this can happen for the parabola that I am looking for? If no, you have to defend yourself. So you expect a parabola that passes through these 2 points. So the parabola should be like this or like that, yes? But let us imagine, let us try it like this. Do you think this will work for this function? If no, why? Yes?
Okay, so in the left part of it before
Before -2, because this
Yes.
-2 is just exactly -2 here.
the slope is decreasing up there. So
here,
yeah, and on the parabola down there, it's increasing technically. Since
no, that's not the reason. Don't get confused again. So you are comparing this. Might be you are
I'm
right,
not
but
thinking
I
about
want
the
to.
slope,
I
I'm
want to.
thinking-
Don't
no.
compare the slopes. The slope on one of them and positiveness or negativeness of the other one, not the slope of them with the slope of here. So let me just repeat it again. You see, before -2, what type of function I am facing? Increasing or decreasing? Before -2,
Increasing.
increasing.
Yes.
So it means that the derivative should be positive everywhere before this line. Yes?
Mhm.
But if this is the case, here the derivative is positive or negative. Why? Not because of this slope, because it is below the x-axis.
Yeah.
This part, the derivative is negative because it is below the x-axis. So if the derivative is negative, it means that the function is decreasing. But you see, in contrary, the function is decreasing. Yes?
So it should be the other way around.
Yes, let me just check this part, for example. This is a little bit more tricky, yes? But that is not hard. You see, from here to here, between -2 and 2, exactly on this interval, which type of function you are facing?
Decreasing.
Decreasing. So it means the derivative is negative. So what you expect for that, the derivative should be below the x-axis. On contrary, I have drawn it in the positive one.
Yeah.
So it means that by this analysis, so I realize that if this is going to be a parabola, it's not in that direction, it is in this direction, but of course we have to more or less convince ourselves more. So you don't need to be precise, but qualitatively you need to respect. So if I ask you this question in the exam, I expect you to draw this and I expect you to fine-tune these numbers for me. You need to specify these points exactly on your graphs. Okay? But now I hope that you agree with me what's happening. Now, let us check it again. Before -2, I am facing a positive, increasing function. Increasing function means its derivative is positive. When I go to the derivative function, I have to face a function which is above the x-axis, so that's correct. And then when I go from -2 to 2, the derivative is negative. Why? Because it's decreasing. The derivative is negative, it means that it is below the x-axis, so that's correct. It's between these two, the graph of the derivative is below the x-axis. And when I pass 2 up to infinity, everywhere the function is going up again. So the function is increasing. Its derivative is positive, so it means that it should be always above the x-axis, and this is it. Yes? So that is squaring with that one. But this one is also tricky, so you will see that this point is a function whose second derivative is 0, and then you expect a minimum for the graph of this function. I think your book hasn't talked about those things, so I don't want to confuse you. But at least from here to here it was not that hard. Yes? But now you repeat the process which already you know actually. Now, do you remember I talked about parabolas and you were able to get the lines? Now you can just ignore the first part and assume that this function is your original function. Of course, this is the derivative, but I hope that you can draw the second one for me, yes? So what I have to do here, what type of function you expect? It was a third-degree polynomial. Its first derivative is a parabola, so its second derivative will be a straight line. Yes? So where this line is passing through? Origin. Yes? Why is that? Because now this one is a local minimum. So this means that the first derivative at 0 is 0. The first derivative of this graph, but this graph itself is f prime. So this means that this is f double prime. Yes? So f double prime of 0 is 0, so this should be a line passing through the origin. And tell me, in which direction, with a positive slope or a negative slope?
Positive.
It's a positive slope, so you can just immediately convince yourself of that, yes? That's also possible. And now, this is a good example. Let us do the reverse order. Okay, how could you go from here to here? Not exactly. The point is that you shouldn't expect to be able to get this thing exactly, because if I give you the function f of x, for example, x squared, yes, what would be the original? Let me write. What can I? So the original function is not exactly known, because so if I tell you that this is the derivative, the function itself is something as a third of x to the power of 3. Do you agree? If I ask you what is the derivative of this, you will get this. But if I give you this function and I ask you what is the first derivative, you still get this one. So this is why if I give you the derivative, there is not clear what the function is. The function is clear up to an additive constant, which is not clear. So this means that if I give you the graph of the derivative, in principle, there is no one single answer to the graph of the function. Yes? But all of those functions are shifted with respect to each other. So this one plus 1 will be shifted 1 unit up, plus 2 will be shifted 2 units up. So that's what I want you to understand. The reverse process, that's not determined uniquely. But assume that this function is given, this graph is given. Be careful, in the exam questions, remember when I draw a graph and give the picture to you, you need to understand which graph is this. If I have written f of x, that is f. If I have written f prime of x, that is the graph of the derivative. Now, how could you go back and detect something like this? This is the question. It's a little bit harder, I think. The derivative is given. You want to predict what will be the behavior of the graph of the original function. It's not that easy, but you should be able to understand something from this graph. You should understand that in the graph, -2 and 2 are important points. But what type of points will they be? Because by looking at this function and the graph, you realize that f prime of 2 is what? F prime of -2 is what? Can you tell me? This is the graph of f prime. And I'm asking, by looking at this, what is f prime of 2? Everyone.
0.
0. Yes? And what is f prime of -2?
0.
0. So this means, do you remember I told you that whenever the first derivative is 0, you get candidates for what? You get candidates for local extreme points. But they are candidates. They might be fake ones, yes? They might be terrace points. And now, so how do you understand they are fake or not? And how do you understand that this should be a max, you see? I'm cheating because I have the graph here. And how do I understand this is indeed a minimum?
Was it the first derivative test?
Yeah, yes, that's the content of the first derivative test, but how should I apply it here in this context? So you see, when I give you this in the exam and you do not have this graph in front of your eyes, I might ask you what are the local extreme points of the graph of the original function. Okay? So then you look for the points for which the derivative is 0. So you get for roots of the derivative, you get 2 of them, -2 and 2. So this means the first derivative of f is at 2 is 0, the first derivative at -2 is 0. Now these are candidates for local extreme points. Okay, how do you understand this point is a minimum, is a maximum? Here you see the corresponding point is maximum. How could I predict this? Yes? Are you doing some report? What you are doing?
No, I'm just blind. I can see it.
Okay. You cannot see the screen. You can come and sit in front rather than doing that. Okay, anyway.
But you know, I can answer the question.
Yes.
You look at the first part of the parabola, and because it's over the x-axis, you know that it's increasing.
Yes?
And then you see that it's hitting 0, so that means that it's a maximum. Because then after, it's below.
Exactly. So what you are saying is, if I want to draw some sine table for this, here I have x, here I have f prime, here I have f. I don't know exact values for f because I told you that exact values of f are not clear because there are infinitely many functions whose derivatives are this. But I know something. I know at -2 and 2 the derivative is 0 here and there. Yes? But now look, before -2, this is my graph, which is above the x-axis, and it is positive. Between -2 and 2, from here to here, the derivative lies below the x-axis, So whatever it is, I don't care. I care it's negative. And then after 2 again, the derivative is positive. Yes? So now you see what will happen. This goes up, this goes down, this goes up. So this is indeed a max, and this is indeed a min. Yes? So if I ask you, what is the local maximum point, we cannot answer that. The only thing that you can write is just -2, and f of -2 is a local maximum point. If you ask me what is f of -2, I cannot give you the answer using this piece of information, because there is no unique answer. So that's local maximum, because if you see it's a maximum, and 2 and f of 2 is a local minimum. Yes? Yes?
Yep.
Okay, now let me make it a little bit more tricky. Okay, so what happens in this situation? So could we more or less understand that behavior? So if I want to go back, yes, by the way, could also I predict this one that it passes here, or no? No, that is not easy for you, because this means that the derivative of this function is 0, but the derivative of this function is the second derivative, and if the second derivative is 0, it means that I have an inflection point. But forget about those things, you just consider about these points. Okay, now I don't know how to ask this question to pique your curiosity. So what I am saying is this. Can you draw the graph in a way that it corresponds to a terrace point for the original graph? Can you draw the graph of the... I don't want you to... There is one feature I want you to point it out for me. What type of point in the graph of the derivative corresponds to a terrace point for the original function? Is the question clear? For example, here, if I ask you what type of points on the first derivative corresponds to local extreme points, you told me the answer. The roots, the zeros of that function, provided something that Hussein actually explained. Now my question is that, can you tell me a graph, can you draw a graph for me, or just describe it for me, so that that point on the derivative corresponds to a terrace point in the original function? So just remind yourself, let us repeat it. What is a terrace point? What is a terrace point? Yes?
It's a point where the slope is 0, but before it's either increasing or decreasing, but at the same time, but at the other side, it's also increasing or decreasing.
Decrease. So a terrace point, you can say a terrace point is a point whose first derivative is 0, because the slope is still 0, but it is neither a local max nor a local min, yes? Okay, so can you just draw something here for me which corresponds to that one, exactly what you are saying? So you want to make the derivative 0. So what does it mean? It means that it should pass the x-axis. But this kind of passage is not correct. This kind of passage is not correct. Because this kind of passage corresponds to what? Can you tell me again? This is the derivative. This kind of passage is related to a local... No, this point. It's not a terrace point. Don't get confused. I am talking... Even if I have a terrace point here, even if I have a terrace point in the derivative, there is no guarantee this is a terrace point on the function. Yes? So that's let us not confuse you. What I'm saying is that, let me just repeat this again. This point A, this point B on the derivative function, not the function itself. So this means that if I see something like this for the derivative, this point corresponds to a local minimum or maximum.
Minimum.
Why? Because before this point, the derivative is positive, and after this point, the derivative becomes negative. So it means the function goes up and down. So this is max. Not here. This is, of course, not a maximum for this function, you see. This is just an ordinary point for this function. But for the derivative of, for the function itself, this is a local maximum. And for the same reason, this is a local minimum. Okay, now can you just be qualitative like that? I don't want you to be precise. So I want to make this point C. I want to make this point C on the derivative graph a terrace point for the original graph. What should I do? So the graph of the derivative should definitely touch at or passes through this point. But if it passes in this form, it becomes a max. If it passes of this form, it becomes a min. So what should I do then? I don't want a max, I don't want a min. Yes?
Maybe a vertical line?
No?
Should
Yes?
I go through all the three?
No. Only I'm considering C now. So for example, this kind of terrace point, you want to have this behavior above this point on the graph of the function. So you told me that the slope is 0. So it means that I have to have this point on the graph. But before that, it is increasing. After that is also increasing. So what can I do? There's only one way to do it. I want to keep the derivative positive. Before and after. So what should I do? You are confused, yes?
Maybe draw a line that starts from the positive side and only goes up.
No. But what happens for the left side then? Yes?
Should it intersect, right at that point, so it shouldn't,
Yeah, it should come here and go back. Yes? Because so it means that I should have a local minimum here. Let me see. If this is the graph of the derivative, let me ask you, what is f prime of c? Can you tell me? This is the graph of not the function, of the derivative of the function. So what is f prime of c by looking at the graph? It's 0 because it touches the x-axis. Okay? But now look. Before c, what is the derivative? Positive or negative?
Positive.
Positive. Don't say negative. I am not talking about the slope. I am talking about this. So that's positive. Before that, the derivative is positive because it is above the x-axis. After that,
Positive.
positive again because it is still above the x-axis. So this behavior happens. So this means that if in the derivative, in the graph of the derivative, you see something like this, if you go up and look at the graph, you see a terrace point up there. Is that understandable? Okay, how should I have a terrace point like this?
The other way around.
The other way around. So for example, if this is D, this I should have something like this. Yes? This point D, which is on the graph of the derivative, corresponds to a terrace point of this type on the function itself. Yes? So if you want, you can memorize, but I want you to understand, yes? So if you have a graph of the derivative, the passages, the zeros are important, where the graph touches the x-axis, touches or cuts the x-axis. If it cuts like that, up there, we will have a max. If it cuts like that, up there, we will have a mean. If it touches like this or that, we will have a terrace point. This corresponds to this behavior, this corresponds to that behavior. Yes? But so this is a good place to understand these things deeper. So I would say that this is good to understand these things. Yes? Is that clear? But so this is what I'm saying. For example, so for example in the exam, I tell you that this is the graph. I don't want to make it very precise. I can just draw something by freehand tool or something like that. For example, I take this one. Okay, and I just draw the graph of the function. Yes? And I tell you that this is not the graph of the function, this is the graph of the derivative of the function. And that, for example, I can give you numbers, I can give you letters. Okay, and then I can ask you different questions. For example, I can ask you, how many local extreme points do you expect for the original function? By the way, look, this is the graph of the derivative. How many local extreme points I expect for the original function? Yes?
3.
3. Corresponding to which points?
A, B, D.
A, B, and D, because these are cuts. Yes? But, okay, up there, do you expect a max or mean?
Which one?
Up there for A, up
Max.
there for B, up there for D.
Max.
A is max because on the left-hand side, the graph is above.
Yeah.
On the left-hand side, increasing the original function. You see, don't get confused. What about this function on the left? Is it decreasing or increasing?
Decreasing.
This is decreasing, but still I am saying it's increasing. Don't get confused because the derivative is decreasing. Yes, but the original function is increasing because the graph is above the x-axis. Yes, so what I'm saying is that before this, the derivative is positive because it is above the x-axis. So it means the original function is increasing. And then after this point A, the graph goes below the x-axis. So it means that everywhere after A, between A and B, the graph is below the x-axis, so the derivative is negative. So this is, as you said, corresponds to a max point. Yes? And then, for the same reason, this corresponds to what? A min point. But this one corresponds to a terrace point. Which type of terrace point?
And increasing.
An increasing type, thank you. This type.
Mama, what was the answer to the terrace point?
Pardon? And then this one, what? Again, this is of this behavior. So that's also a maximum.
I understand.
Yes? So I don't know, might be we can connect these things together somehow and draw the graph of the previous one qualitatively, yes? Because here we have a maximum and then we are supposed to have a minimum and then we are supposed to have a terrace point and then we are supposed to have a maximum. Something like that, you know? So we were able to guess that this is qualitatively the graph of the original function. Is that understandable? Yes?
It's very inconvenient that it intersects the x-axis. What happens if it doesn't? Or they just...
No, if it doesn't, what does it mean? If the graph of the... So that's also a good question. So what happens? So it means that that's a boring graph, yes? So if we do not have intersections, let us see how it goes then. So for example, let us consider this scenario. So I have let us consider a parabola like this. Y equals to x squared. No, sorry, not x squared. This is a parabola, but this is the graph of the function, for example. Okay, so what do you see for what happens? That's a good question, by the way. So what happens for the graph of the original function? Is there something interesting we can say about that? Yes, Hussein?
Is it just terrace points? I guess.
No, there are no terrace points. Terrace points corresponds to a touch.
For touch.
Yes, touch, being tangent to the x-axis. No touches. So do I have a terrace point for this, for the original graph? No. Do I have a local max? Do I have a local mean? So what do I have?
Straight line?
Not a straight line, but something clear. Yes?
It's increasing. Or
It's always increasing. It's a function. Why? Because you see the graph of the function is always above the x-axis. So it's the boring increasing function everywhere. Yes? We cannot say more than that. Yes?
Does the original function intersect the x-axis?
No, we don't know about it.
We don't know that.
No, we don't know. There are some functions which intersect the exact. We don't know. What we know is that we have a function which is all the time increasing. Yes?
But it's not a straight line.
Pardon? It's not a straight line. But then I am thinking that because every third degree polynomial should have a terrace point. Sorry. It should have an inflection point. No, not terrace point. So this is one of those types. So no inconsistency. Everything is right.
Can you try to draw it?
So if you want to draw so this means that at this point that you haven't studied, because, by the way, this you should know. If this point is A,
Yeah.
if I ask you what is f prime of A and I give you the ruler, where do you measure to answer this question? This is the derivative function. Where do you measure? I give you a ruler and I ask you to measure somewhere to give me the answer. Where do you do that? This is the graph of f prime.
You look at the height.
Yeah, exactly. So why you're hesitating? So you go up and get this one, and then this is your height that you measure. But now if I ask you, so this I don't know, it depends to the length. But if I ask you, so if this length is b, I answer b. Yes? But now if I ask you what is f double prime of a?
Is your phone ringing?
Yes? So what is f double prime of a? Yes?
0.
0. Because what is f double prime? F double prime means f prime prime, yes?
Yeah.
So if you consider the g in your head, this would be the graph of g, and I am asking what is g prime of a? It means that what is the slope of the graph, of the tangent to the graph of g at point A? And that is 0. Yes?
Yeah.
Okay. So this is 0, definitely. But this I have to have my ruler to measure this or whatever. Okay, but now you are telling me that, okay, if I want to draw some graph, this should be related to this is you haven't studied, because if the second derivative turns out to be 0, I will have an inflection point. Inflection point means, so you see this is an inflection point. Why? Because before this point, the function is concave down. It's like an upside bowl, yes? And then after that, immediately it is a normal bowl, yes? So the inflection point is a point, the convexity of the function changes, yes? So this means that whenever I have this, I have some scenario like that up there, okay? Yes. So it means that I should have, but that is a little bit strange. So the graph should be like this, because you know that a terrace point is also an inflection point. If I draw it like this, before that, it is concave down, and immediately after that, it's concave up. So it means that it should be an inflection point, but not a terrace point, and on the time, always increasing. So it should be up there. It should be something like this. If this is horizontal, so it should be a graph like this. Something like this, you know. I should keep it an inflection point, but I have to be careful not to make the tangent horizontal. And I have to keep it all the time increasing. And that would be this function. Something like this. Yes? Okay, so I think now you have good understanding about these things. So sometimes they give you the function and you are supposed to find the graph qualitatively, not exactly, yes? So this is also good success. You see, if I give you the graph of the function, derivative of the function, by understanding these behaviors, you could expect that you should have something like this, yes? Yes? And then I connect it to a minimum, then I have to connect it to the terrace point like that, and I have to connect it to a maximum continuum, yes? And that's also reasonable, yes? Because after this point, you see the function, the derivative is negative all the time, so it means the function itself is decreasing. And everything is consistent. So when you see this, the original function is of this form. Not exactly, we don't know, but this is the general features of that. Is that understandable? Okay, so that is the lesson for today. I will update the Google Classroom so that you can work. There is one part left from this chapter which is very important. So far, do you remember when we studied about, I don't know why they have postponed it in this book to this chapter, because that's not an application of derivatives. I would rather to teach it in the previous chapter, because in the previous chapter we learned about derivatives and we learned how to differentiate different functions. There is also a very important function which is an exponential function. We want to know how the derivative of an exponential function works, yes? So I would say that this is rather a part of the previous chapter. It's not an application of derivative, yes? Okay, but I just want you to know one part is left, and that's a big part because I want you to understand it fully. But for the exam, it is very simple. This is one of those lessons that I present, probably takes 2 sessions. But we reach to one single formula that you can use it, okay? The reason that I go through it, because I want you to understand what is happening rather than just memorizing the formula, okay? Okay, so yeah, I will stop the recording here. And I will write the Google Classroom which pages we're supposed to work. And I think I really want you to go through the book itself, because it also gives you some good commands in GeoGebra. It's always good to have GeoGebra in front of you, be able to explore things yourself. Okay, thank you.